So what we have here is the definition of an alternating series, and our assumption is that we're dealing with these ANs here. They're non-increasing, so they either stay the same or they get smaller from term to term, and they're all positive. And if we take these and we take the first and then subtract the next and then add the next, then subtract and then add and then subtract and then add, you can write that as a series using this sort of formula here. That's what we call an alternating series. So let's take a look at what that partial sum sequence would look like on the number line. So here's 0 on my number line, and what we could do is we could see this as addition, then subtraction. So first, here's my addition. So I'm adding a 0, and if I add a 0 to 0, that's just going to be the first term in my partial sum sequence. So here's a 0. Then I'm going to subtract a 1, and because it's non-increasing, it's going to land somewhere to the right of that 0. So there's a0 minus a1. And then I'm going to add a2. So add a2, land somewhere to the left of this a0 because a2 is a little bit smaller or the same as a1 to get to this point here, so on and so forth. And so what's going to happen is we're going to have these alternating terms converging in towards the middle. But while I use the word converge, the question is, does it actually converge or does it keep bouncing around left, right, or does it kind of converge down to a single point? And that's where the alternating series test comes in. The alternating series test about, well, alternating series says, and we could generalize this notion of an alternating series just a little bit. First of all, there's no reason for convergence that we have to start with a 0 term, and also because we're just going to be multiplying everything by a negative, the convergence will not be affected if we start with, say, n plus 1 and the exponent of the negative 1, or n minus 1. Actually, that would be the same thing. So this is our alternating series, and it converges when the limit of the terms an go to 0, and it diverges otherwise. This is sort of like the divergence test, which says that a series diverges if its sequence limit is not 0. However, the alternating series test goes a step further and says that the series actually does converge when the sequence, ignoring the negatives, the sequence of positive non-increasing terms does actually go to 0. We can say it converges for the limited case of an alternating series. If it's not alternating, we can't use that fact. Let's talk a little bit about why that works. Well, first of all, it diverges when the limit's not 0 for the same reason as the divergence test. It's just really just using the divergence test again. It's a little bit more complicated with the negatives, but not really. In fact, let's just take a look at what this looks like in the picture. Picture-wise, it's actually easy to see why that would be the case. Because if the limit is going to 0, then the things we're adding and subtracting are getting smaller and smaller and smaller. And what's going to happen is we're going to get this whirlpool until eventually it does converge down somewhere in the middle. All right, that's the picture if the limit is equal to 0. All right, what if it is not 0 though? Well, what's going to happen is that it's going to keep going around in a circle, but it's never going to go meet anywhere in the middle. It's just going to keep going here to 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 here. It's not going to converge to any single point here in the middle, and that's why it diverges. Okay, so let's put this to the test with a couple of examples. we're going to show that the alternating harmonic series converges. And so the harmonic series, let's remind us what that is. Remember that the harmonic series is the series k equals 1 to infinity, 1 over k. So 1 plus 1/2 plus 1/3 plus 1/4. And that diverges. Okay? But it turns out that if instead of adding, you just subtract every other term, it actually changes to converges. And we can prove this using the alternating series test. All right? All we have to do, we can rewrite this just a little bit to see that this is an alternating series of the form. We have a -1 to the n plus or minus some k, and then we have our terms 1 over n. These are my ANs. So all I need to do for the alternating series test is to say, what is the limit as n goes to infinity of my 1 over n's? Well, that's 1 over increasingly large numbers. That does limit to 0. Now, the only other thing I should make sure of, and it is the case, first of all, these are positive, and they are decreasing, which means they're non-increasing. They're getting smaller and smaller for bigger numbers n, non-increasing. We're good to go there. So, because we have alternating series, this is positive and non-increasing ANs, and the series test says just take the sequence, ignore the negatives, just get rid of all of that in our head, and just take the sequence and just make sure the limit is 0. The alternating series checks out, therefore the series converges. And really quick, I'm just going to draw you a picture. This is no longer part of the example, but if you were to try and see what this looks like, 0 to 1, all right, then we have to subtract 1/2, so minus 1/2. If we add a third, that's going to go up to 5/6, excuse me. Then we subtract a fourth, then a fifth, and then we go back and forth, back and forth. Eventually, it's going to converge right here. Now, what's important to note is that we don't know what it converges to. All we know is that it does converge, and often that's all we really care about. But fun fact, this number is the natural log of 2. All right, and that we can't use the alternating series to prove this. We would have to use more advanced techniques to prove that. That's not a homework problem though, so don't worry about that.